Okay, let's start. Can you hear me? Is it working? Where do I turn on this? It seems working, but the voice is okay. Hello, 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 hello. Is it okay? Yeah. So, okay, ignore those parts. Those are not true. So today's final review session, and I'll just first make some announcement, same as before. So the main point is don't take everything we said for granted, because we might be wrong. And some announcement. So as you all know that the first two exams takes 25% of your total point, and the final exam is 35%. So we haven't finalized all the questions for the final, but the total point could be somewhere around 120 to 150. I guess last year was 140 something. So it's more time sensitive this time. So you still have 3 hours. And so 2/3 of the exam will be from lecture 28 to the last lecture, and about 1/3 is general questions, including all the previous lectures. Okay, and we have extra office hour on the day before the exam, on Wednesday in Hausen 110, the lecture room. And don't forget the joke contest. So the deadline, I changed it to the morning, like right before you take the exam. So I guess maybe some of you will be studying on the overnight maybe. So maybe some good ideas will pop out so you can still submit your jokes. So reminder, first place got 2 points, and second place got 1.5, and third place got 1 point, if I remember correct. And last thing, don't forget to do the survey that is already posted on the Blackboard. And another reminder is, if you recall that the last lecture, which is given by Dr. Vogelston, he actually asked you to do something. You need to spend an hour to do a meditation stuff. So that will be actual final exam question. So you can lie or not lie, but he'll grade that question. So the actual exam should be technically 4 hours instead of 3 hours. All right, I guess that's all. Just last night I was looking at the Piazza. This is the number of posts on Piazza, and you see that 2 clear peaks, which is the day right before the 2 exams, and I'm expecting another peak right there. Okay. So today's plan, I guess Andy will start first, cover Dr. Zhang's part, and then Ali will cover Dr. Kulin and Dr. Zhang's old lectures, and then Miguel will cover Dr. Wang's part, and I will cover myself, and also all the general questions. So I won't go through all the previous lectures, but I'll do a summary and checklist. So if you have further questions, just raise your hand and ask. We'll explain more. Okay, now you want to use your, only have the HDMI.
Okay, so I'm going to go over Dr. Zhang's part from lectures 32 to 35. So from lecture 32, the first thing he went over was recurrent networks. So this is just a definition of recurrent networks, or a fully recurrent network, which is where each node in the network, which represents a neuron, is potentially connected to all other neurons. And the reason why we use recurrent networks in modeling like neuronal networks is that in a neuronal network in your brain, each neuron potentially synapses with all the other neurons. And so these red dots represent like axons from all these other neurons that potentially synapse with that neuron at each of the red spots. And then each neuron can also potentially synapse with itself. So basically every neuron in the network can potentially synapse with every other neuron, and the strength of their synaptic connection is the weight ij represented in a recurrent network. So a particular type of fully recurrent network that we used in this class is the Hockfield network. And so on the left, the Hockfield network is defined as the state u sub I of each unit or each neuron I follows a differential equation, which is the time constant rate of change times the rate of change is proportional to the negative current state that it's at plus the weighted connections of all the activities of all the other neurons that it's connected to. And the reason why this kind of makes sense intuitively is that if you consider a particular neuron I, right, how much it should change based on how much all the other neurons are firing should be subtract its current state to kind of set the expected rate of change to 0, and then how much it should change after you subtract its current state is how much all the other neurons are giving it information. So that's kind of the intuitive understanding of this differential equation. And then to get the equilibrium activity of all the neurons, you just set the expected rate of change to 0, and then you get that the equilibrium activity is going to be equal to basically the weighted inputs from all the other neurons that it's connected to. Okay, so then this is the construction for the Hockfield network as a model of how we store memories. So if we have a bunch of different memory patterns, basically the weight in the weight index ij in the weight matrix is going to be proportional to a particular index I multiplied by a particular index j in the same memory. So this notation is kind of misleading. Actually, sorry, it's not misleading. So we have a memory pattern S, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, whatever represents the different information in that memory. So in the case of your homework, it was whether a pixel was black or white. So black was, I think, +1 or -1, and white was the other one. And then, so weight index ij stores a proportional amount of information that index I is related to another pixel j. So we'll revisit this. But this weight construction is the reason why Hockfield networks are robust to input noise and connection damage, and we'll see why in a couple slides. So then in order to store multiple memories, you just simply add the product of index I and index j in all the other memories. And so basically, instead of writing it out like this, we wrote it out in matrix form like this, where if we have capital M number of memories, each memory with capital N number of states, then we can concatenate all those memories into this column. We can concatenate all the column vectors into this matrix capital S. And then we can construct the weight matrix by taking S, multiplying by its transpose, and then averaging it over the number of nodes each memory has. And this matrix form is essentially all the Wij's constructed like this. Okay, and then when you construct it like this, we noted that the weight matrix was symmetric. So I think understanding how to construct this Hockfield network by adding all the product ij's of each of the memories is pretty important, and you guys have done this twice now, I think, like on the most recent homework and on one of the homeworks at the beginning of the year. Okay, so the main reason why this Hockfield network is a good representation of how we store memories is that each of the memories that's used to construct the weight matrix ends up being an eigenvector of that weight matrix. And basically, like, if you think about how your memory works, when you see a situation or an object or a representation that was similar to something that you had seen before, you recall that exact same thing or something similar to it. And that's kind of how an eigenvector works, right? When you multiply a matrix by its eigenvector, you get the same eigenvector out scaled by an eigenvalue. So this is just the proof of that. So we're trying to prove this, that when you multiply the weight matrix by a particular input that happens to be the eigenvector, aka a memory that you use to construct the weight matrix, you get that same memory out. So for now, ignore this approximate orthogonality part and let's just go to the bottom. So if we take a particular memory that we use to construct the weight matrix S and we multiply it by the weight matrix, the first thing we should do is substitute how we constructed the weight matrix Wij, right? So we said on the previous slide that Wij is constructed like this. So we literally just substitute that expression in here. So now we have two summations. And then what you can do is isolate, or since summation is linear, you can swap the order of the summations and isolate just the parts that depend on j, and move the part that depends on m to the front. And then what you notice is that for a particular index position j, between two memories m and k, because this pixel might be black or white with equal probability across multiple memories, on average you can expect the product of these when you sum them to equal 0, right? Because there's an equal likelihood that the product of the same pixel position in any two given memories, assuming that the memories are independent, when you sum across all the memories, it has an equal likelihood of being positive 1 or negative 1. So when you sum across them, the expected value should be 0, except for the cases where m equals k or k equals m, right? Because in those cases, you're summing the product of the same pixel position in the same memory, so it's for sure going to be 1 because that pixel is either going to be 1 times 1 or negative 1 times negative 1. And then this proof here was that random walk proof showing that when you multiply the same pixel position but in the same memory, those are the ones that equal 1, so they don't sum to 0 on average, and then that approaches like root n or something. So basically when you do this, it just shows that if you go over the proof on your own, you basically prove that when you multiply the weight matrix constructed by the memories and you multiply that weight matrix by one of the memories that you use to construct it, you get that memory back out here. But I think if you didn't understand what I just said, just understand that if you use a memory to construct a weight matrix, that memory is going to be an eigenvector of the weight matrix. And on your homework, we were just exploring different properties of that eigenvector, right? So the idea here is that if you input a noisy input, which is roughly similar to one of the memories that you use to create the weight matrix, you still get an approximation or the actual memory back if the noisy input is close enough to the weight matrix. So on your most recent homework, it was like changing 20% of the inputs to was it like the opposite color or a noisy color or something? And then when you put that into the weight matrix, you get a really similar looking memory out. Yes?
It's also true that for a weight matrix that's n by n, that by definition means you have n memories stored, right?
No. If the weight matrix is n by n, you don't know how many memories are stored. You only know like the dimension of the memory, right? Because if you think about the most recent homework, the memories you were storing were 40 by 40 images, right? So that's 1600 pixels. and your weight matrix is 1600 by 1600. So the reason being that, so S, right? If we look at how S is constructed, there's capital M memories. So in the most recent homework, there were five different 40 by 40 images you were storing. So capital M was 5. And each image was 40 by 40, so it contained 1600 pixels. So capital N was 1600. So your vector S was 1600 by 5, and then S transpose is 5 by 1600. So then you get a 1600 by 1600 weight matrix.
In this case, your memories are vectors.
Yeah, the memories are vectors.
So they're directly related to the number of columns, right?
No, the number of columns. So you vectorize the 40 by 40 images, so it's a single column vector, and there's 5 of those, so you concatenate them side by side. So the number of columns is just how many total memories you have, and then the number of rows is like how big that memory is, or like how many pixels the image is in the case of the homework. So the size of the weight matrix does not directly tell you how many memories were used to construct that weight matrix.
But it also tells you the maximum number of eigenvectors.
Correct.
And considering those are memories,
Correct.
it also tells you the maximum number of memories.
Potentially, yes. It tells you like the capacity of eigenvectors you could potentially store in that weight matrix. So there's this like optional slide that he had that was like, if you construct a Hockfield network in this way, you can only store like 14. The number of memories you can store, so capital M, can only be like 14% of the size of each individual memory, but that's optional material. But I think that's what you're referring to, right? Okay. So basically, like all properties of eigenvectors apply because we constructed the weight matrix in this way. So basically, if you provide a vector that's close enough to the eigenvector, when you multiply that noisy input by the weight matrix, you get approximately the eigenvector back. So that was like question number 1B or something on the homework. And then similarly, if you take the complement of one of the memories that you use to construct the weight matrix, I think this is problem like 1C or 1D or something, the eigenvalue will just be the negative of what it was before, and you'll get the same, you'll get a negative of the memory that you used to construct it back. So if you think about the homework, if you pick like one of the images and you put it in, you just get the flipped version of the image back. So basically, if you just understand the entire Hockfield network as an matrix and its eigenvectors, then you can derive all the properties from it. Okay, so these are the properties. So it's robust to input noise and connection weight damage. And I think there was a question from one of the homeworks in the beginning of the semester about why this is the case. So if we think carefully, we're storing 40 by 40 images, so that's 1600 pixels. And we're only storing 5 of them. But we have a weight matrix that's 1600 by 1600 just to store 5 images. So if we think about what each row in the weight matrix, what it represents, each row will contain all the information about how that particular pixel position I is connected to all 1599 other pixels in all 5 of the other images. So that's why even when we destroy half the weight connections in the weight matrix, in reality we're only destroying like half of the pixels, half of the information for how pixel I is connected to all the other pixels across 5 images. So even if you destroy 800 connections about pixel I, you still have 800 other connections about how that same pixel I is connected to other pixels. And so that way you can still get information about whether pixel I should be white or black, because even if you destroy 500 connections, you're not actually destroying a ton of information, because there's a lot of redundancy in the network, basically.
Does the column store any information about that pixel?
Both, right? Because it's a symmetric matrix. Yeah. Okay, and then the Hockfield network, each eigenvector represents this discrete stable state that the network wants to return to when you provide an input vector, which is why when you provide a noisy vector, you return to one of the stable states, which is one of the memories that you use to create the Hockfield network. And then the idea was that this loosely models Hebbian learning, because in the construction, in Hebbian learning, it's something like neurons that fire together wire together, and that's kind of represented by this. When two states are the same state, their weight becomes positive, basically. Okay, so that was it for Hockfield networks. Does anyone have any questions? I think if you guys want to review Hockfield networks, maybe the best way would be to go back and like understand the homework from a high level as opposed to like what the coding was about. Yeah.
I'm not sure if this is just semantics or not, but when the memory states are not random, so
yeah, when
we're assuming a random memory state, and that basically proved the eigenvector.
Yes.
Because of the random walk.
Yeah.
Increasing with the square root. But for example, on our homework and stuff like that, it doesn't have to be the case where half the around half the memory states have to be
correct.
Or negative one. So I'm just curious because that randomness is a very pivotal proof of the Hockfield network in general. But I don't feel like that holds.
Okay, so I think it's more about the independence of the memories. So even if you look at a particular pixel position I, like you're right that like in the images that we looked at, it wasn't the case that half of the pixels were black or half were white. Some of them were the case, but for example, like the letter A, there was many more white pixels than black pixels. But as long as across all 5 memories, each pixel has an independent probability of being black or white between any 2 memories, then it's valid to use a Hockfield network. The restriction being that if it's not exactly half white and half black on average across all independent memories, then the limit of how many memories you can store will decrease. Does that make sense? Because if you have half black and half white across all of them, you have like maximum entropy in a sense. So you could potentially store like the most number of memories into a matrix of that size. But if it's not all half black and half white, you can still get the eigenvector property, but you just won't be able to store as many memories. Okay.
Do we need to know how to derive the maximum number of memories stored?
No. That was like empirically determined, so you don't need to know how to prove it.
What, do we need to know how much it is?
No. Okay. Okay, so the next topic that he went over were like how we locate ourselves in space, so like spatial localization. So basically in the hippocampus, there's 3 different types of neurons that help us figure out where we are and what orientation we're faced in. So this is the summary first, and then I'm going to go into each one. So first, he went over the head direction cells, where the firing rate of particular neurons depended on which direction your head was facing. So this was kind of analogous to like a compass. And then it's modeled by a reading attractor, which we can kind of go over later. And then the second type of cells were place cells, where the firing rate of each individual neuron depended on what spatial location in your local neighborhood you were in. So for example, like in this room or on this campus, like wherever I walk, the firing rate of particular neurons will increase depending on where I am. And then finally, there was these grid cells where maximum firing rates appeared at periodic spatial locations, and that each of these spatial locations had this like hexagonal periodicity to it, which we'll see a picture of later, and that additionally there's like different scales of these hexagonal shapes. And all 3 of these types of cells have in common that they use a world coordinate system, in the sense that their firing rate depends on a coordinate system that's not centered on yourself, it's centered on the world around you. And they can all be corrected, or they're all somewhat dependent on familiar landmarks. And additionally, they also depend on information from your own path integration through self-motion, and this can occur through multiple inputs, for example, like knowing your body, knowing how many steps you've taken and how long your stride length is, or taking into account like vestibular information from integrating like your acceleration through your vestibular system. And then a good analogy that I read for how the place cells is related to your grid cells is that your grid cells is kind of like the lines on graph paper except imagine that this is like a continuous graph paper that wraps around and connects to itself, and then the place cells are like specific intersections on the piece of graph paper, and you use both sorts of information to kind of know where you are in the world. Yeah.
The grid cells are two-dimensional then, but in map space?
The place cells?
No, the grid cells.
No, so you can, so we'll see in a couple slides, they model it with a torus attractor. So it's like you take a two-dimensional space, and then because there's no boundary conditions, you wrap the boundaries around itself to make a torus, basically. We'll see in a couple slides. Okay, so first going over the head direction cells. Basically, each one of your head direction cells is tuned towards a particular head direction. Head direction is kind of misleading. In reality, it should just be like the direction that your head is pointing in the external world, because head direction implies that like, actually it is head direction. I take back what I said. It's just whatever direction your head's pointing in, a particular neuron will have a higher firing rate for that direction. So the picture that he gave was this mouse that's like walking in a trajectory, and every time the head of the mouse points in a particular direction, the neuron that's tuned towards that direction fires with a higher firing rate. And since there's a continuum of directions that you could be looking in the world around you, like 360 degrees, you can model it as this ring of overlapping tuning curves. So if your head is pointed in a particular direction, there's multiple neurons that could potentially fire with different firing rates to encode that head direction that you're pointed in. And that's how you can get a continuum of directions with a finite number of head direction cells, right? Because technically there's like infinity head directions that you could be pointed in, but you only have a finite number of head direction cells. And so the way you know what head direction you're pointed in is the weights of the firing rates of the head direction cells that you're pointed in. And then one property of the head direction cell is that you can use landmarks to help you gauge where your head direction is pointed in. And so, for example, like if I know that this door is on my right and I'm looking forward, and I know that's on my right, then when I turn, I can use the difference between where the door is and like where my head is now to help me gauge where my head is. However, additionally, I can simply integrate like how much my neck muscles had to move my head in a certain direction to know the angle that my head turned. And I can use both sorts of information to help my head direction cells know what direction my head is pointing in exactly. Because sometimes there's errors in how well you integrate your muscle movement, in which case external information about the world around you that is fixed can help you correct that error from self-integration. And basically the experiment was that when he turned the lights off and there was no more landmarks, the head direction cells for this mouse with head direction north still fired, even without the landmark information. But then basically there are some other experiments where if you confuse the mouse by like making it dizzy or something and then pointing its head in a particular direction, sometimes there is error in the mouse's head direction cells about where exactly it was facing. But then when you reintroduce, when you do the same experiment with a landmark, there's less confusion because the mouse is taking into account that it's oriented in a particular spatial reference to the landmark. And an idea about how this works is that, or basically the idea is that, how do you have a sustained high firing rate for a particular head direction even when you're not moving? Yes?
So if you move the landmark, do you say now it's fire and it's re-encode what like your placement is to landmarks, so not to know where your head is directly?
If you move the landmark but the mouse doesn't move, I would say that the same head direction cells fire. But if you like confuse the mouse and you move the landmark, then it's not necessarily the case that the same head direction cells will fire. Because remember, it takes into account both information, like how it moves relative to the world around you, as well as like landmarks in the world. Yeah.
So which one took priority in that case?
So in the case that like I don't move my head, but like say like someone breaks down this door and then reconstructs it like a little bit to the left, like I still know that I'm facing that direction, right? But if you like spin me around and make me really dizzy and like disorient me and move the door, then I'm not entirely sure what direction my head is facing. Are there any other questions about head direction cells?
I'm going to have to use that equation on the bottom right to look for any question.
I want to say unlikely. I think this is just more for a deeper understanding of how you have a sustained firing rate even when you're not moving. And the idea is that if you have some external input, in this case like visual input or input about how you've moved in the past, so integrated motion input, that into a particular neuron, if it's tuned to your particular external input, there will be a high firing rate. But the idea is that in this ring of head direction cells, they're all connected to each other, where there's no connection for neurons that are far away, and for neurons that are close by, there's this like lateral inhibition so that you can get really specific tuning for what head direction you're in. And not only that, you get because this is an equilibrium state, when du dt is 0, you get a sustained stable firing rate that's dependent on how the other neurons are firing, multiplied by their weighted connections to the particular head direction neuron that you're at. So basically you can use something like a Hockfield network to model the activity of head direction cells. And basically the idea of the ring attractor, which is kind of confusing and not that necessary to understand how head direction cells work, is that the possible stable states where your population of head direction cells can be firing is a continuum. So it's like 360 degrees and all the intermediate degrees in between all those degrees, right? There's like a continuous spectrum of directions your head could be facing in. But when we use a Hockfield network to construct how memories work, each memory was a discrete state. So they weren't related to each other, and you can't move continuously from one memory to the other. You can only make discrete jumps. But in this case, as I'm turning my head, I can make continuous, I can have a continuous change in firing rate across my entire population of head direction cells. And so that's why we use this model of a continuous ring attractor, where the possible stable states are this entire continuous spectrum of directions, which is a ring. Yes?
On the lower right, is it just one cell, like that image?
This image?
Sorry.
Oh, this image?
Right. Is it just one cell firing, or like?
Yeah, it's like this one cell firing.
Okay.
Yeah. And this thing isn't like the firing rate. This thing is the connection weights.
Okay.
Yeah. Okay, and then so here's a little bit more about head direction. Basically, the idea is like, how do we take information from the external world around us, aka landmarks, to help us correct which head direction cell is firing. So for example, suppose you had a population of head direction cells mapped out as this line from 0 to 360 degrees, and suppose that at some point this head direction cell around like 270 degrees is firing, but it's just after I've like moved around and integrated some information, possibly with some error. And then I see this door that's this input from my view detector. What that input does is that it actually bumps the highest firing rate to the correct position that I'm actually facing, 180 degrees. And so basically this is the idea that even if as I'm moving around, I might integrate my movement incorrectly, and then I can use external information from my vision and stuff like that to correct the exact direction or the true direction that I'm actually facing, and have the head direction cell that's tuned to that direction actually fire. And basically, Zhang was talking about how there needed to be some shift from the direction I thought I was facing at to the true direction, because there's a shift in this firing rate peak, right? and he said that was kind of like a wave traveling to its true position, and the traveling wave can be modeled by an asymmetric lateral connection weight. So on this slide, you had this symmetric connection weight, which produced this really stable firing rate, right? But in this case, if I'm taking into account other information, I need to shift my stable firing rate to another position. So the idea is that maybe this is like an asymmetric lateral connection. But then you face a contradiction, because in your population of head direction cells, like you don't change, like physiologically, you can't change the connections between them very quickly, right? Because as I'm turning my head, I like know what direction I'm facing like almost immediately. But in order to have a stable firing rate for a particular direction, if I'm not moving, I need to have symmetric lateral connections. And yet, if I'm going to be able to take into account landmarks, I have to be able to move this peak, which suggests asymmetric lateral connections. And you can't have symmetric lateral connections and asymmetric lateral connections, right? So basically, he talked about this alternative model where you had these like head direction cells for moving towards the right and head direction cells for moving towards the left, and they have fixed connection weights to each other, but they take information into account from both groups when deciding which head direction cell to fire. But I don't think you need to know the details. Basically, it's just that when you have asymmetric lateral connections, you produce this traveling wave at equilibrium as opposed to a fixed position when you have symmetric lateral connections, like in this case. However, this asymmetric lateral connections is a poor model for how we correct our head direction cell firing, because we can't actually change our connection weights really quickly in real life. So there's an alternate model. That's like the big picture. Okay, so then the second type of cells that we use to locate where we are in space is place cells. So this one's pretty intuitive. Basically, the potential stable states that we can be at is now a plane in 2D as opposed to a ring. So then basically, even when there's no input, for example, when you're not moving, there's sustained activity at the particular place you're in. For example, you had this mouse moving around a room or a maze or something, and then basically the neurons that represented the particular coordinate positions that mouse was in 2D fired at a higher firing rate and a stable firing rate when the mouse wasn't moving wherever the mouse went in that room. And then, like the head direction cells and the grid cells, it took into account self-motion, potentially from vestibular input, but also maybe from other sources that would drive that firing rate bump to each new location. And they also use landmarks to correct its errors. And then what they found was that these place cells had a boundary. So like, for example, the place cells that represent this room in my head, like as soon as I walk out of the room, like I'm in a new place, right? So like how do I create this like new place that I'm in? And so the idea was that there's these grid cells that basically represented this sheet attractor, but without boundary conditions. So if you took the sheet and you took the boundaries and you connected them to each other, both on like the x-axis and the y-axis, you get this torus shape, which is basically like, as long as wherever I walk in the world, the representation of where I am doesn't have any boundaries, whether I walk like infinitely in that direction or infinitely in that direction. And so basically I like never have an edge of the world representation in my head for the grid cells. They basically shift wherever I move. And yeah, that's modeled by a torus. And then basically they found a representation in our brain of that, which was the grid cells. Yeah, are there any questions about head direction cells, place cells, and grid cells?